Here are solutions to homework set number 13 for ECE 341. This homework looks at t-tests with two populations. Now the first problem is I've got two players, X and Y, playing a dice game. X rolls 5 10-sided dice, Y rolls 2 4-sided dice, 3 6-sided dice, 4 8-sided dice. High score wins, X wins on ties. What's the chance X is going to win? Well, one way to do that is a Monte Carlo simulation. I'll roll the dice one time, find X's score, find Y's score. If X is more than Y, X wins. Repeat 100,000 times. If I do that, X wins 26% of the time. So that's one way to calculate the odds of X winning. That requires 100,000 rolls though. Can I do it in fewer rolls? And sure enough, the answer is yes. But that needs some statistics. Suppose I just roll the dice 4 times. So I'll take 4 measurements for X, 4 measurements for Y, and that's what this does. I start with a cleared matrix, clear X and Y, and then add to it the previous results. This is a little bit inefficient, but when you're running at 4 gigahertz, you don't really care. When you're done, here's the scores for X, there's the scores for Y. To find the probability that X wins any given game, find the mean of X, standard deviation of X, mean of Y, standard deviation of Y. Now create a new variable, W. W is the difference between X and Y. W has a mean, that's just the difference between the two, so the mean is minus 4.75. On average, X loses. The standard deviation is the sum of the variances of X and Y square root, 9.86, and what I'm looking for is the number 0. What is the area to the right of 0? Because this is where X beats Y, misspelled Y, and this is where X loses to Y. Well, to determine that, I find the t-score. How far is 0 from the mean in terms of standard deviations? The t-score is minus 0.48. Go to a t-table. For example, here's the t-table. I have a sample size of 4, so I look at 3 degrees of freedom. The number I'm looking for is minus 0.48. So that'd be over here off the t-table. I could also use StatTrack to convert that to a probability. The probability is 33%. So with only 4 rolls, I'm actually pretty close to the true odds. What if I use 20 rolls? Here's the same procedure. Roll the dice 20 times. I get 20 measurements for X, 20 measurements for Y. From them, find the mean, standard deviation, t-score. I now use the t-table with 19 degrees of freedom. So I come down on the t-table, 19 degrees of freedom, and I'm looking for the number minus 0.4895, which again is going to be over here. Or I can use StatTrack. StatTrack converts that to a probability of 31%. Finally, let's roll the dice 100 times. With 100 times, I'm not going to print out the results, but it has a mean, standard deviation, t-score. Now on the t-table, I go to 99 degrees freedom, basically 100, or go to StatTrack, corresponds to 28%. So here are the results. The true odds, well, almost the true odds with Monte Carlo, if I roll the dice 100,000 times, X won 26% of the time. If I only roll the dice 4 times, I can come up with a pretty good estimate for how the probability of X winning. As I roll the dice more and more, I get more and more accurate. And these numbers will vary. They're random. But I don't need 100,000 rolls. So that's kind of the idea of a t-test. With t-tests, I can start doing some kind of interesting things. For this website, I can test my reaction time. And kind of here's how it works. I click on here, wait for the light to turn green. When it turns green, I click the left click. So that was 308 milliseconds. Repeat. 316 milliseconds, and so on. Take 5 measurements. Now, change the condition. So the way I changed it is I just ran the test a second time. Is there learning going on? Do I get better with practice? So take 5 more measurements. That's population B. I want to find out, is there a difference? Do I get better with practice? So to do that, I've got two populations. Find the mean standard deviation. And again, here's the trick. T-tests really only work with one population. So turn the two populations into one. Create a new variable W that's the difference between A and B. A minus B is 20. So my reaction time got less the second time around. The standard deviation is the sum of the variances, square root, 36. And what I'm looking for is how far is this number from 0? That's my t-score. The t-score is 0.56. Using StatTrack, I can convert that to a probability. I have a sample size of 5, meaning 4 degrees of freedom. 0.56 means 30% chance. So there's a 30% chance that my reaction time is going to be worse after practice. 70% chance it'll be better. That's for an individual. In terms of populations, for populations, you divide the variance by the sample size when calculating the standard deviation. So now the t-score is 1.2. That gives a chance of 13%. So it's 13% chance my reaction time gets worse with practice, 70 or 87% chance that it gets better. Another test over here. There is the AIM trainer. Kind of a neat website. There it is. What you do is you move the mouse around, point at the target, and you repeat this 30 times, and then tells you your average reaction time. So I did that 3 times, got average reaction time of 752, 661, 758. I then tried my non-dominant hand, got 3 reaction times. Now let's run a t-test. Is my dominant hand quicker than my non-dominant hand? Well, again, same thing we did before. I've got 2 data sets. Find the mean, find the standard deviation. For a new variable W, the difference between the two. W has a mean. Here the mean is minus 270. There's the number 0 over here. So over here, this means my dominant hand is better. Over here means my non-dominant hand is better. Faster reaction time. What's this area? To determine that, I find the t-score. The t-score is how far is the mean from 0 in terms of standard deviations, is 2.9 standard deviations away. And here I can actually use the t-table that's on that. I've got 2.9 standard deviations, sample size of 3, meaning 2 degrees of freedom. I'm looking for the number minus 2.9. That's right here. So 5% chance, or from StatTrack, 5.3% chance. 5.3% chance my non-dominant hand will beat my dominant hand in reflexes on a trial of 1. For population, which hand is better overall? That's a population question. When dealing with populations, you divide the variance by the sample size. And now I'm 5 standard deviations out. Going to the t-table, 5 standard deviations is right around here, about 1.5%. Or using StatTrack, actually 1.8%. So there's a 1.8% chance my non-dominant hand is quicker than my dominant hand, or 90, whatever the minus that is, 98.2% chance my dominant hand is better. That's just with a sample size of 3. So that's kind of what a t-test does for you. It lets you compare two populations, and I don't need 100,000 rolls. I can get pretty good results with just a few rolls. Like in this last example, with only 3 measurements, I can be pretty sure my dominant hand is quicker than my non-dominant hand. And that's homework set number 13 for ECE 341.